Okay, we'll be talking about eigenvalue and eigenvector for our session 13. So eigenvalue and eigenvectors are also very important qualities in a matrix and talking about linear algebra. So we'll be talking about what they mean and how they apply to a lot of our understanding of linear algebra and how it's applied to finding some properties of matrix as well. Okay, so move on and we'll keep on going here. So, what is an eigenvector and values? We need to know about the definition before we start knowing about the properties of these of these values. Okay, so given a square matrix A, a scalar lambda is called an eigenvalue of A if there exists a non-zero vector V such that this hold. So what does this mean? So basically, there could be some cases where we multiply matrix A into a vector V. Somehow the value it gives us is the same as just multiplying a scalar lambda into V, right? I'm trying to think about if there's such a case like that, although I can't think of it right now. But there could be some cases like this, okay? Like most of these cases would be like where matrix is actually just like a scalar, so it's like a 1 by 1 matrices. So this should be like 2V. And then we can let this lambda be 2. And that would be the same, right? But this is just for 1 by 1. But there are cases where we multiply a matrix, but then the same as just multiplying a scalar value into the vector V, okay? So we'll be talking about these cases. And if this holds, while V being non-zero. So we don't care about if V is 0, because if V is 0, this holds anyway, so it's not really important. It's not that important to know about the cases where V is 0. In that case, lambda can be anything. So we only care about the part where this equation holds for some non-zero vector V. Then we say that this vector V, this non-zero vector, is called eigenvector V, A, and it corresponds to the lambda, which we call eigenvalue. So if this case holds, and V is not 0, then we call this lambda. We call this lambda as eigenvalue, and we call this V as non-zero, and we call this eigenvector. All right. So this kind of shows that, in a sense, I wrote some things down. So basically, like the action of a matrix only stretches or compresses the eigenvector without changing its direction. So kind of way, because remember, like when you multiply some value in a vector, if you think about it in like a physics term, vectors like usually denoted with some having like a force that has direction, right? So it's like a force where it has like a direction with an arrow. So what this is telling us that what this matrix does is that it does not change the direction of the vector. It just merely stretches it, right? By multiplying lambda. So the direction of the vector does not change, but the force kind of changes. So like basically it stretches the vector. So it's like an intuition there. And lambda is the factor which we denoted by eigenvalue, which allows the eigenvector to be stretched or compressed. All right. So that's like the definition here. So we now have to compute the eigenvalues, okay? So how are we going to compute the eigenvalue? And this is where the determinant comes into play. We talked about how we can use determinant to get the eigenvalue in vector, right? Excuse me. So we're going to talk about how we use determinants. So remember that we used to have this notation where we had an AV as lambda V. Well, and what we want to do is find lambda and V. Think about this. Just turn this thing onto the left, and what you get is this should be right, I think. You write it like this. So in order to find lambda and v, we remember that v must be non-zero. And what we can see in this equation, we can think of this part as also a matrix, right? A minus lambda I is a matrix, right? So this is like a matrix here. And suppose that this matrix has an inverse, then what happens? If this has an inverse, you can multiply the inverse for each side, and what you get is v is 0. So in this case, we get a unique solution where v has to be 0, so there's no eigenvector, because eigenvector has to be non-zero, right? But if this vector has a inverse, this shows that v cannot be non-zero. So v has to be 0. So if this part has an inverse, we can show that there is no such eigenvalue or vector satisfying this sort of equations. So in order for this to have an eigenvalue or eigenvector, it must be the case where this matrix does not have inverse, which is same as saying this determinant, the determinant of this matrix is 0. So what we have to show is that the determinant, that's right here, is that the determinant of a minus lambda I has to be 0, and this must hold to find the lambda and the corresponding eigenvector. Alright? And that is written here in number 1 about the process of finding and computing the eigenvalues. To find the eigenvalues of a matrix A, we must solve the characteristic equation like this. And what I mean by characteristic equation is that actually it's not that difficult. We just say like those sort of like notation where we have a determinant of a minus lambda I is equal to 0. We call this equation characteristic equations. I don't think you can see this, but we call this the characteristic equations. It's on the slide. So, and it's an equation because basically we're solving for some determinant where we don't know what lambda is. So lambda is like a unknown parameter like x, and we are setting it to 0, right? So it's like an equation. And remember that I is like an identity matrix of the same size as A, and lambda represents the eigenvalue. And we're just doing that. We're just multiplying identity matrix to lambda, because without it, lambda is not a matrix, so we cannot like define the subtraction or addition matrices. So in order to make sure it holds, we're just multiplying lambda with an identity to make that sense, to make that into a whole matrix. Okay. All right, then we can solve this, and we'll show you an example how to solve this. And if we solve this, we'll be able to find the lambda, right? The eigenvalues. So if we solve this characteristic equation, we'll be able to get the lambda. And if you get the lambda, now you need to substitute this lambda into the equation and get the v, right? Because remember that we had the equation here. Basically, a minus lambda I times v is 0, right? But now since we have the value for lambda, we can just plug it in, the lambda value, and use it to solve for v. So we can now get the v. So once the eigenvalue have been found, you just use it and substitute this into the equation, and then use it to find the vector v. And if you find this non-zero vector v, we call this the eigenvector, corresponding to the lambda, which is eigenvalue. So eigenvalue and eigenvector go like 1 to 1. So for the eigenvalue, there's the corresponding eigenvector, and eigenvector, there's the corresponding eigenvalues. Oh, no. Okay. So we'll use some example to talk about this. To see what this kind of means, we'll start by giving some actual example for a matrix A, which is a 2 by 2 matrix. Like that, it's like 2, 1, 1, 3. All right. I'm going to find the eigenvalue and eigenvector of the matrix. So first step, we have to find the eigenvalues. So to find for eigenvalue, we already said that we have to solve for determinant a minus lambda I. And this becomes like the one written in the bottom, and this is because you already know, but let me just write it. So we're solving for a minus lambda I, and we know that lambda is, we know that a is basically 2113, right? Was it? Was it 2113? Yeah. And we minus it by identity, where identity matrix for 2 by 2 matrix is this, right? And if you do subtraction, what you get is 2 minus lambda, 1 minus lambda, 3 minus lambda. So it becomes one matrix like this. I hope you guys can see it. It's on the slide, okay? And you're making sure that this determinant is 0. So we have to choose like lambda that makes it into 0, okay? And here's some exercises you can use. So for the exercise, you're trying to solve this. But let me just, before we go on to the exercises, let's just solve this question. So basically what we would have is that we have to solve this question of determinant. So just write it up here. Excuse me. All right, let me just write the thing here. So we're finding determinant for 2 minus lambda. Oh, you can't. Oh, you can't see this. Sorry. I'll write it a bit more below here. Okay. Determinant 2 minus lambda, 1 minus lambda, 3 minus lambda is 0, right? And we just solve for the determinant, which is easy now by this time. You can already know how to do this. You multiply diagonally and subtract them. So we get 1 minus lambda, and this is 0. I want these hard equations. So lambda square minus 5 lambda, right? And 6 minus 1 plus lambda equals 0. So we have lambda square. Oh, and there are some cases where there might be no solutions, or sometimes, or maybe like to be exact, there's always solution if you think about like a complex number for eigenvalues, but let me just go on with this equation. Because I'm not sure if this is going to have a quick answer here. Does this have an answer? Because I'm thinking this has like a complex solution. Right? Because, yeah, it's going to have a complex answer. So it's going to be something like, yeah, so the answer for this, like, it's going to be like, lambda is going to be like some complex number, you know. Like, you might be familiar with this concept, like you have some value and then you have plus, minus, and I, you know. Like complex value, but this is also the answer. So what I'm trying to say is that you have to do like this sort of proving the equation, and you've solved the equation, you'll be able to get the lambda you want. And if you use this lambda, surprisingly, you'll be able to get the case where you multiply a by b, you get lambda b. And since you already know what lambda is, you use it to find the vectors, okay? All right, so this is kind of the way you do it. Let's move on to exercises. So we have an exercise here. We're going to find the eigenvalues and eigenvectors of a matrix also here. So let's try also solve for exercise 1. And for exercise 2, you can do it you can do it like if you want in your own time. We'll try to just solve for exercise 1 after you guys think about this, and just pause the video and think about how to solve this, okay? Excuse me. Okay, so we'll solve exercise 1. We needs to find eigenvalue and eigenvectors of a matrix. So how we solve this is simple. We do the same thing over and over again. So we have to find the determinant for minus lambda I. Do this again. It's like just doing things over and over again. So you get determinant for 3 minus lambda 2 4, right? 4, then 1 minus lambda. Okay. So we're solving this. Well, do the. I hope this gives me like no non-complex value for answer, because I kind of want to just solve it using like the real numbers for these cases. But the answers can be kind of complex answers. So let's see. 4 lambda, 3 minus 8 is 0. So lambda squared minus 4 lambda minus 5 is 0. Oh, this has answer, right? So you get the answer where the answer is, can you see it? Yeah. The answer is, can you see why? Yeah, simple equation, polynomial equations, right? So basically, it's lambda minus 5 times lambda plus 1 equals 0. So lambda is either 5 or minus 1, right? So you have 2 lambdas, okay? Lambda could be 5 or minus 1. Now, since you got the lambda, let's try to find the eigenvector as well. Should be one for each eigenvalues. Let's do it for 5. Okay, so we're going to have some sort of vector, which is going to be v1, v2. And if you multiply this, you have to get something like, let's just do it for lambda 5 for now. So we have to have this 5v1, 5v2. And we kind of, because this is just like 2 by 2 matrices, let's just solve it like doing like the normal equation. So it's like 3v1 plus 2v2 is 5v1, and 4v1 plus v2 is 5v2, and you get, let's see, what do you get? 2v2 is minus 2v1. Also, sorry, 2v2 is 2v1, so v2 is v1. All right. Oh, so what this tells us is that we have v1 as v2, right? So what this means is that basically, as long as you have an element where v1 and v2 are same, all these non-zero values are going to be like the eigenvector for this eigenvalue 5. See? Let's try. You can plug in, for example, let's say it's 1. So let's say this is 1, 1. And this should be 5, 5, right? Because we multiplied 5 to vector 1, 1. You can see that if you do the equation here, you're going to get 5, 5. So all these like v1 and v2 vectors, where if the vectors all have same number of elements for v1 and v2, they're going to be eigenvectors. So there can be like multiple eigenvectors for one eigenvalue, just be noted. And let's also try for minus 1. So v1, v2, we have minus v1 and minus v2 now, because as I said, we're multiplying minus 1 into the equation because minus 1 is now the eigenvalue we're thinking of, and we also can solve this like this. So what you get is let's see. Okay, 4v1 is minus 2v2. So 2v1 is minus v2. What does this give us? Oh, same thing, right? So, yeah. So, what this got us was 2v1 is minus v2. So all the elements where 2v1 and v2 has this equation, they can all become the eigenvectors. So what this kind of tells us is, like, even though we solve for like just two eigenvalues, there could be the eigenvectors doesn't have to be unique for each eigenvalues. There could be multiple eigenvectors. It could be possible for some one eigenvalues. Okay, just remember that. All right. All right. And I'm not going to solve for exercise 2. You can just try it. Because it's 3 by 3, you can kind of imagine this is going to be a bit more difficult. So but like difficult in the sense that it's not like hard in a mathematical sense. It's like it just takes a long time to do the computation. So if you want to, you can try it, okay? But it's going to give us like similar answers like this. Okay, so when can we use this like eigenvalues or vectors? We're going to talk about this using some of the examples. First is about non-singularity. We talked about why, like, if a matrix has like a linear independent column vector, we call them non-singular, and otherwise we call them singular, right? We can actually just use the eigenvalues to kind of show that holds, because actually, if there's some sort of matrices, we can compute the eigenvalues, and if any of them are 0, then there's a bit of a problem there, because it's going to be singular. For example, in this case, for 2, 1, 1, 3, you can see that this is going to be non-singular, because you can kind of see the column vectors are not, well, they're not linearly dependent to each other, and also because we already kind of know, because the determinant of this matrix you can kind of calculate easily, it's going to be non-zero, which means this has inverse, which is also saying that this matrix is non-singular. Or also you can check the eigenvalues for this. So, and by the way, like determinant, you can see that this is 5. This is like determinant of the matrix. And let's check the eigenvalues, which is, we have to do that equation thing again. But if you're more used to the equation for getting the lambdas for eigenvalues, you can kind of do it very fast by just plugging in the values for lambdas and just getting the determinant, which is going to be like this, right? Do the multiplication, you get lambda square, 5 lambda, and you can kind of see that it's not going to give us like the, what you call that, it might not give you like the complex solution, but sometimes you can kind of check that it's going to have non-zero element. And you can see, like, in this case, the eigenvalues are all non-zero, because remember, like, when you have an equation, when you check like the coefficients and the constants, they are like the multiplication of the right answers, which is like the values of lambdas. So we're multiplying 2 lambdas, and because we're not getting zeros out of it, we can kind of see that the lambdas are not going to be 0. So in a way, if you compute them and see that the lambdas are not 0, we can say that the matrix is non-singular. Okay? All right. And we can kind of see that if you multiply the eigenvalues, the same as the determinant value. But we're not going to go in too deep about this. If you want to know more about it, you should check out the linear algebra classes, okay? Oh, and we also talked about this. I already solved this, but let me just briefly talk about it. So we can get the characteristic polynomial for this function, which is what written on the slide. So we can get the polynomial, and if we solve this, we can kind of see that the two eigenvalues are not going to be 0. And because neither eigenvalue is 0, we can say that the matrix is non-singular, which is like another way to say that the matrix has an inverse. Okay. And we can also talk about positive definite of the matrix. So what does it mean for a matrix to be positive definite? Okay. And we usually talk about this. In this case, the V is not like a symmetric matrix. Oh, and by the way, I wanted to talk about like another notation that I forgot to mention, which is symmetric matrices. So what is that? So symmetric matrices are the matrices where the even if you switch the row and column indexes, you get the same value. So for example, so if you write it in a more abstract way, you'll be writing something like, if A is a matrix, and this is A11, A12, A21, A22. What do you mean when you say it's matrix symmetric? Is that even if you change the row and column index, they're going to be the same. So in this case, this one, 2, 1, and 1, 2, if you switch the indexes, they're still the same, which means these two elements are going to have same value. In this case, we call that the elements are symmetric, and because the elements are symmetric, you can kind of easily see that A and its transpose are going to have the same value. Okay. When we talk about positive definiteness of a matrix, we usually talk about like symmetric matrices. So I'm just going to assume that the matrix is kind of symmetric. So in this case, what does it mean for a matrix to be positive definite? So basically it's like this. So let's assume that A is like a n by n matrix, and X is like an n by 1 matrix, and we think about X transpose, where X, then if it's transpose, then it's like 1 by n matrix, right? So if you do this, if you multiply these three elements, you're going to get a scalar value because it's 1 by n, n by n, and n by 1, so you get a 1 by 1 value here, right? We sometimes call this like quadratic transformation or quadratic form. I don't remember the exact name. And we say that matrix is positive definite if for all x, this is positive, where x's are all positive. So what does it mean to be a matrix to be positive definite? Is that as long as x is non-zero, so as long as x is not 0, if you do this multiplication for any sort of vector x, you can multiply to a. We're going to always get a positive value. Okay, so if that happens, we call this matrix like positive definite matrix. Okay, nice property. And the reason is related to eigenvalues, that actually we can say that a matrix is positive definite if all of its eigenvalues are positive. So interestingly, if all the eigenvalues are positive, that matrix is positive definite. Interesting, right? So basically, if you want to show that the matrix has a positive definite property, you can do like using the very rigorous definition, which would be using this quadratic form to show that the matrix has like indeed a positive value. But another way to show it is that just compute the eigenvalues, and if you can check that this matrix indeed have a eigenvalues that are all positive, we can say that the matrix is positive definite, right? So continue, like this shows how it works. So basically, we're doing it for the B cases. So we can get the determinant and you can get the answers. And from the answers, we can show in the computation that the two eigenvalues are all positive. And because both eigenvalues are positive, we can show that we have shown that the matrix is positive definite. They're like a one-to-one relationship. So if matrix is positive, all of its eigenvalues are going to be positive. And if all the eigenvalues of a matrix is positive, then the matrix is also positive definite. So very, very nice quality. Okay. And in economics, we use a lot of the time for a matrix to be positive definite, because positive definite, remember that all the eigenvalues are positive. And as I told you, like the determinant of a matrix is same as multiplication of eigenvalues. So because eigenvalues are all positive, that kind of implicitly mean that matrix is going to have a non-zero determinant, which means that the matrix has an inverse, right? So when you say like a matrix has a positive definite quality, it kind of means that the matrix has an inverse, which means that whatever equation we're solving is going to have a unique solution, right? Okay. And here's some of the exercises. You can determine if the matrix is non-singular, if the matrix is positive definite, or if the matrix with trace 7 determine 10, what can you infer about this eigenvalues, okay? So I'll talk about some of the exercises, like 1 and 2, and some I'll leave it as like something you can toy around with, okay? So we'll have some short break, and then we're going to talk about these exercises, and we'll end the session, okay?